Imagine uncovering a vulnerability so critical, it scores a 9.8 on the CVSS scale. Intrigued? Keep watching to see how I dove deep into the Windows kernel to unravel this mystery. It all started with the latest Windows patch on August 13th. The target, TCP/IP.sys, the kernel driver responsible for handling TCP/IP packets. With little documentation available, I knew this would be a challenging yet rewarding journey. My first step was to reverse engineer the vulnerability. I found a few exploit write-ups for older bugs, but nothing substantial. When the top search result is in Chinese, you know you're in for a tough ride. Despite Google Translate's mediocre job, the post provided detailed insights into IPv6 fragmentation, giving me a head start. Later, I stumbled upon an analysis by Axel Souchet, which went deeper into TCP/IP.sys internals, helping me define several undocumented structures. The patch analysis was surprisingly easy. Usually, it takes days or weeks, but this time, it was instant. There was exactly one change in the entire driver file, and it turned out to be the bug after all. A BNDIF overview showed that only a single function was modified. Typically, I'd go through 20+ function changes, but not this time. The function IPv6 pprocess options had a single line of code changed. This was a clue that the issue was with some kind of list. Microsoft sometimes adds functions like feature $2,660,322,619 private is enabled device usage 3 to enable partial patch rollbacks. This setting allows an administrator to unpatch a single vulnerability without uninstalling the entire monthly patch rollup. The patch replaced a call to ipSendErrorList with ipSendError, hinting that the issue was with a list. Reverse engineering the patch was only half the challenge. The rest involved understanding the codebase and crafting a request to reach the target code. The change was in IPv6 pprocess options, indicating it involved processing IPv6 options. A quick look at the IFC told me what an IPv6 option is. Using the Python library, Scapy, I crafted a test IPv6 packet to reach the vulnerable function. After setting a breakpoint on TCP/IP, IPv6 pprocess options and running the script, it was clear that an empty option structure was enough. Adding invalid options to the structure triggered the call to ipSendErrorList. Almost any invalid option formatting could do this. The code iterates a linked list and calls ipSendError on every item. The problem occurs when ipSendError is called on a list item other than the first. Understanding the list was challenging. I lost days to reverse engineering parts of TCP/IP.sys, but Axel's blog post was extremely helpful. The pointer passed to IPv6 pprocess options is a linked list of packets. Setting a breakpoint revealed the list contained only one packet. IPv6 fragmentation allows senders to split large packets into smaller ones, which made sense to keep together in a list. After extensive reverse engineering, I confirmed my assumptions. The fragment list is not related to the one we're dealing with here. Accidentally, I found that the list would populate when the kernel was paused, causing the network adapter to accumulate packets. This behavior is likely a performance optimization. At low throughput, packets are processed individually, but at higher volumes, they are organized into lists. To trigger the DOS condition, I needed to flood the system with bursts of IPv6 packets. This would get a nice big list passed to ipSendErrorList. Using Python in a VM was slow, so I reconfigured the target VM to use only a single CPU core. This made the packet list contain lots of entries. ipSendError disables the packet by setting net_buffer_list greater than status to hexadecimal C000021B and transmits an ICMP error back to the sender. I found a code path in ipSendError that sets the packet underscore size to 0, leading to a potential race condition. By setting the option type value to any number larger than 0 by 80, I could trigger the always_send_ICMP condition. The IPv6 fragment parser was a good place to look for vulnerabilities. An underflow in the EAX register could lead to a buffer overflow. Although I didn't find an RCE, I discovered a way to leak kernel memory, leading to an ASLR bypass. And that's how I unraveled this critical vulnerability.